it automatically records. You go to the pre-recording Matterhorn, or you can go to any lecture on Friday and it's just a black room.
Is that right?
Yeah, this automatically records it. So
wait. So you go to.
Oh, so we have lectures in ComSci 340 in this room.
Oh, I see.
Monday, Wednesday, Friday, and on Friday to Easter.
Oh, I see. It was just empty. Oh, it's black. Oh, because the lights were.
Yeah, the lights were.
I see. Okay. Right. So, out of curiosity, the student interface to the lectures. When you go to the lectures, what is that through? Is that through Pause, or is that through
this, or what you
the lectures for classes in general, the Matterhorn lectures?
We get emails. It's like a new lecture video has been posted.
Okay, so that's what I get as well. I just wasn't sure what the student interface is.
Blackboard.
Right.
I have Blackboard like flag, so.
Moodle or Blackboard?
Blackboard.
Really? So you have to go to Blackboard.
No, you don't have to. You don't have to, but if you want to, you're in Blackboard. You click the link when it opens.
In the email.
Yeah.
So you can go through the email, or you can go to Blackboard, and you've got all the lectures there. Okay, that's
But not Moodle.
right. Okay. So does that mean there's a kind of a stub of a 371 class site in Blackboard?
Yeah. Oh yeah. All the ComSci classes.
Every class at the UFS has the same.
On Blackboard. Okay.
All the ComSci ones are
And
usually stubs because we.
in this case, all it does is it lists the lectures that are recorded on Matterhorn, I guess.
It does, but you don't have any associated lectures. It only posts the ones that they're actually posted.
No, I mean, so when Matterhorn records a lecture, you said it's available through Blackboard?
Yeah.
And so it lists them.
Below, not in the class, like listed below all your classes.
Oh, really?
Yeah, it's really unorganized. It's not.
So you mean it's like intermingled, like class A, class B?
I only had one class. I don't know.
What do you mean? It's organized?
Like 340, 371, 340, 371.
I think so, yeah.
For the lectures.
I think so.
Okay.
Well, on the Matterhorn interface, it'll say view other videos in this series or lecture series.
I see.
So that you can see all the
Okay, that's helpful. I apologize for going into that. It's just I'm never clear on what students get for Matterhorn, and so I wasn't clear if I need to create my sense is that it was distributed to all of you automatically, and that seems to be the case. It's not always as nice an interface as I would have hoped for. Okay, so today we're going to be talking about testing for object-oriented systems. We've talked about path coverage and multiple types of path coverage. Give me the basic steps involved in testing with path coverage. Identify what you want to cover. Good start.
develop paths that encompass what you want to cover.
Good. Legal paths that, well, yes, legal paths that go from start to finish. And kind of almost part of being a legal path is, and you have to be able to start that path at some place that you can get to from the start and go to some place that finishes. And what's the final step?
Create test cases from those paths.
Man, you folks are doing well. Okay, so I'm looking forward to marking the final. Yeah, really. Okay. And I can take the minimum for the team or something like that.
No, just one test.
Okay.
It's a team class. A team final.
Okay, well that's an interesting, interesting notion. Okay, but we're going to be talking about object-oriented systems in this sort of post-path testing lecture. I'm hoping to see some elements of this make their way, if not into your actual testing infrastructures, then at least into your postmortems. what we could have done.
There's lots.
I hope that this material will serve use, and maybe it will make it into some of the last-minute tests that I hope are being put into place, because that's an area where additional strength was needed last time I looked. Okay, so we're going to talk about object-oriented testing needs in particular. You folks were probably still in swaddling clothes when, no, you weren't even born in the early heady days of object-oriented programming. There was a lot of hopes laid out that object-oriented systems would enormously reduce the burden associated with testing, because they would allow for, among other things, composing pre-built components, reusing pre-built components in a way that would mean that you're building things out of fully tested components. Just like you don't have to test every new 2x4 you buy at Home Depot structurally to make sure it's sound. There was a hope that we would be able to build programs out of components that were largely tested. We'd be able to extend classes that have been largely tested, and thereby avoid a huge amount of testing burden. And there's a real sense that we might be moving beyond the point where the heaviest burdens of testing programs will now be in the past. Unfortunately, object-oriented systems have very distinctive risks associated with them. And some of these lists are given here. Encapsulation, subtyping, polymorphism, going along with that later dynamic binding, inheritance and subclassing, separate from subtyping issue, and type parameterization, generics and templates, as it might be familiar to you from languages like Java on the one hand and C# or C++ on the other hand, we call them templates. Fundamentally, testing for object-oriented systems can call upon different testing regimens and priorities than testing other sorts of code. The principles of path testing that we've been talking about still carry over to the methods within object-oriented code, but we have a richer set of issues that also need to be discussed. So I'm giving you this lecture because there's some real risks associated with object-oriented code, and a sense of where things may be defective within that code can really allow for more effective testing, more efficient testing which leverages the limited amount of resources available, the limited time, the limited energy, the limited effort you have at your disposal, and puts it to things that really matter in the program. So I have a list of common OO-specific failures here and some challenges associated with them. But I'd like you folks, on your basis of your experience and reflection of what you know about object-oriented programming, to make some suggestions. What are some problems that you think might be associated with the object-oriented program that would lead to vulnerabilities within that program? What could go wrong in an object-oriented system that's a reflection of the fact that it is object-oriented, beyond what might be expected from any code base? Yes, well, vulnerabilities. So fraudulent subtypes, I'll call it, just to be consistent with my previous terminology. So violations of the LSP. Other things? Let's go with substitution principle. We'll talk about this one in quite a fair bit of depth. Others?
I saw clips of the slides. You can't block the
Yes. Yes. Good eye. Good eye. That's a problem, a barrier to testing. It's not so much a vulnerability per se, it's a barrier to testing. You can't lock out a superclass. In other words, normally when we want to do unit testing on a component of our program in an object-oriented context, we have the opportunity to mock out other classes on which it may depend. So maybe we have an instance of class A And to get its work done, it needs instances of class B, instances of class C, and instances of class D, normally. And we can, to do unit testing of this instance of class A, which uses B, C, and D, we can create a mock of B, C, and D. Create mocks of each of those that observe the same interface that A is expecting, but they make use of a mock instead. And those mocks are very useful because they allow us to examine the behavior of A by in and of itself with respect to very simple interactions with B, C, and D. For example, situations where the mock to C might just return fixed values. The mock to D might further test the consistency of some of the parameters passed to its methods and do something very, very simple. Maybe log calls to it also. And the mock to B might be similar. So the point here is that when we are testing particular components of object-oriented systems, we can take advantage of mocking. Do people remember this? Okay. Memoryless processes exhibit many nice processes, many nice characteristics, and they're easy to analyze. I find it very disconcerting to encounter memoryless classes. Are people comfortable with mocking? Okay. We've talked about it a couple times, and silence is ambiguous. It can either indicate assent, or it can indicate being spaced out, or it can indicate having your attention focused on phones, or other misplaced attentiveness. Okay, I'm going to assume you understand what I'm saying, because I now am going to build on this to talk about superclasses. So when we have a superclass, we have not only a situation where polymorphism applies, a subtyping relationship, but we may have A depending on B's mechanism because A is a subclass of B. We have it reusing its mechanisms, its implementation. We have it undergoing inheritance. And in these cases, B cannot be mocked out. It's the superclass of it, and you can't mock it out. You can't have calls from A to B go through a mock instead of directly to its superclass. That's just not something that's possible with today's mocking technologies. Does that make sense, Alex? You exhibit discomfort.
I can see how it can work in some compiled languages, but in dynamic languages like Python, I can see mocking in superclasses. Sort of making sense, but I'm trying to think of a decent counterexample. I guess suppose if there was heavy reliance on the determinism of the superclass, it would be
Indeed, indeed. So if there's fields of the superclass that would be, say, in C++ called protected methods or protected fields, they might be accessible by a subclass and therefore frobbed internally to this class, and therefore you might not be able to catch it so easily. And there are complications, and that's one of the complications associated with object-oriented systems when you use subclassing, is that you can't mock these things out. But how about other vulnerabilities? So fraudulent subtypes is one of them. Another, I would argue, would be subclassing issues, and there's going to be a whole set of those. Another set of issues have to do with encapsulation, issues having to do with problems with the fact that this is more of a challenge to testing, but we may have issues with so-called yo-yo problems, where control, when we have a class A that's a subclass of B, we call to A given method in A may call a method in B, and then the method in B may call a method in A. And so you get this kind of bouncing up and down of control that can lead to confusion about what's being called and can lead to bugs being called. We saw that with add and add all. Remember that in a lecture on subclassing. Encapsulation can hide illegal values within objects that are faulty interaction of methods between the subclass and superclass. Let's just talk about some of these things. You can refer back to these slides for those. Let's talk about some of the major ones that were listed there. One is encapsulation. Within object-oriented systems, we make use of encapsulation. We hide details behind interfaces. And we do this for very good purposes, to achieve modularity, to allow different people to work on different components of a program, but count on what the behavior is of the other components, even if people, so A may depend on B through an interface, and therefore depend on what it does, but not the details of how it does it. And that gives the implementers of B the freedom to evolve that, etc. It means that they can count on what will be provided by B long before it's written, and therefore be able to write code against it. So object-oriented systems distinguish an object's type from its implementation details. In other words, they distinguish the contract, the promises being made by an object from how those promises are carried out, how they're actually achieved. Now, there's a lot of benefits to this: modularity, separation of concerns, and greater user clarity, what is promised, what will be promised in the future, not just now, but what will be maintained, and the flexibility for the creator to evolve implementation that's not promised. These things are all A1 good things. As one former student in this class would have said, they are chocolatey goodness in and of itself. That's been maintained in this class since that point.
Why is this a feature of object-oriented programming?
It's a good question.
It's like a functional program.
Okay.
Sure that you have a contract about your functions, say type signature.
This is a fine question, Alex. And as I glanced at this slide, I found myself musing about why I put this specifically in a lecture on object-oriented programming. You're absolutely correct that the ideas behind this are not conceptually restricted to object-oriented programming. And in fact, we can use these same principles, encapsulation and specification-based design, separating the interface from the implementation. We can use those for other sorts of systems, like functional systems, like procedural systems, for that matter. The fact is, historically, the recognition of the need to separate interface from implementation often went along with the shift towards object-oriented systems. So one of the first computer systems languages to support it was CLU, a cluster-oriented language. It was sort of an object-oriented language, proto-object-oriented language. And these ideas became really emphasized within the object-oriented programming community. And so you're right, it's not limited to it, but it is a prominent feature of object-oriented programming, the aspiration to separate interface from implementation. Okay, it just became a very, very notable theme within object-oriented programming. But conceptually, it's not limited to it. But given that most of our object-oriented programmers aspire to this, the challenge here is that encapsulation can, in some cases, inhibit traditional approaches to testing. So specifically, the fact that we hide details, hide implementation details within a given instances of a given class, prevents us from kind of going in and inspecting externally all the details of what's going on within that class. Information that might be useful for testing whether it's operating correctly. Okay? So when we have a test harness that drives one of our components, so maybe we have a test harness that, for example, drives this instance of A because we want to test it. In that case, we might be putting A through its paces. We might initialize A, call some methods on A, and then want to know, has it computed those methods in the correct fashion? Have the correct algorithms been run? Were the correct intermediate results calculated? And if A is an object which we can only access through a public interface, that may prevent us from reaching in and inspecting these sort of private components of A in a way that would allow for more transparent testing. as a result, in this context, we often turn to things like test hooks, ways of providing methods, like a testing interface for A, that lets us have extra methods that look at some internals of A, like whether or not a certain invariant is being respected, so-called representational invariant is being respected for an instance of A, etc. We may provide test code as part of this class subclass definition. So we build in test methods to the class. That's a good practice. And we may have clear statement and sort of methods to check the class contract, particularly things like invariance and history properties. We may want to build those in. So encapsulation prevents us from seeing all the details of an instance of the class. And that can get in the way of testing. And so we end up putting into place extra mechanisms for this. A second issue has to do with polymorphism. So speak, use, describe to me, characterize for me what polymorphism is.
I'd say it's a class that's, polymorphism is when there's a class that has common shared, I don't know how to put it. They share a common, say for instance, an animal.
Okay.
All animals eat, sleep,
Yeah.
drink.
Good.
And then that class can be subclassed into like a dog,
Yeah.
which barks, a
Yeah.
cat that meows.
Okay.
So the
Okay, you've gotten some important elements of it. It certainly often has to do with capturing commonality among these. But it's actually more specific than that. We often do that through type hierarchies, hierarchies like this. This is from Java standard edition libraries. When we say that we can treat this thing in a polymorphic fashion, what does that mean?
One type being substituted.
Good. And specifically, we can pass around a subtype as if it were an instance of a supertype. So we can pass around a queue as a collection. We can pass around a queue as an iterable, or indeed a queue as an object, right? This is something we do day to day. This is, one might say, our bread and butter as software engineers. Now, when we have polymorphism, it gives us a lot of advantages. It lets us reuse the code created for the supertype against the subtype. And so we can program against the apparent type, as it's called, program against an iterable, and really get a queue, for example. So we can reference a collection, the actual concrete object would be an array list. We have a reference to a dictionary, but the actual object is a hash table, for example. Now, as we've noted before, the catch here is that the dispatching, so to speak, the actual methods that are called are a function of the actual type. So we call perhaps a get method in our what seems to be a dictionary, and it calls it in the hash table, right? We call a get in a collection, and it actually calls it in the array list. So these sort of type hierarchies and polymorphism give us a lot of benefits. They capture understanding, notions of commonality among things, just like Sage said. They allow us to reuse code through polymorphism. The same sets of code can be reused for all the different subtypes. For subtypes that aren't even in place when that code is shipped, can now be used with the same set of code, right? We can use code written with respect to collections with our subtypes of collections, which were not, ladies and gentlemen, a speck in the cosmic eye at the time that they shipped, Java SE 1.6, right? And it gives us a certain amount of extensibility through applications of what's called the open-close principle. The problem here, as Alex articulated earlier, is that of fraudulent subtypes. So misplaced use of subtyping can easily create classes that are not behavioral subtypes. In other words, that violate the Liskov substitution principle, which he quite rightly captured as sort of the essential criteria. And in this case, if we have these subtypes that don't adhere to the promises, ladies and gentlemen, of the supertypes, we can get situations where the subtypes break the code of the supertype. Code written against the supertypes. So all this code that was tested before with respect to supertypes suddenly breaks. And that code, which seemed well-founded and well-tested and indeed fully functional, now no longer works just because we, years later, have introduced a new subtype. It doesn't work with respect to that subtype. And in this case, we fail to ensure behavior of the supertype that's relied upon by a client. So we can't view this code as sort of having been thoroughly tested on a persistent basis. When we introduce a new subtype, we have to retest it against it. Now, specifications in these areas, these contracts, by making them explicit, we can help give guidance as to what is guaranteed to instances of a class, and it can help point out for us things that are definitely not allowed that we can actually test. So often going along with these contracts that we use to reason about subtyping, we use specifications to delineate those things, and then we can use these specifications to formulate assertions and formulate good tests to make sure that these things are being guaranteed. Okay. So in this context, we want to use assertions which test classes against their own specification. If you have a contract, explicit or implicit, you should be thinking about encoding those things with assertions. Those are things which are assumed to be held true as preconditions, I should say. Testing preconditions with assertions. Testing invariants with assertions. Testing postconditions with assertions. Testing history properties with assertions. These will verify that the things that you're counting on for this code to work, your assumptions are being in fact observed, and they will help to document those assertions. So even if you folks give me code bereft, ladies and gentlemen, bereft, absent specifications, absent clear contracts, which I fear that you will, I would ask you, please, I would implore you, please, I would command you, please put into place assertions which at least check those assumptions automatically. Okay? Which at least document those assertions and lend me confidence, lend me faith, lend me conviction that you actually are testing the foundations on which you're building your object-oriented programs. Yes?
To what extent would you recommend assertions in languages with broken type systems like PHP, where I guess it's close to duck typing, but it's not really duck typing? So would we want to check to make sure parameters are of the right type, or is that getting a little bit too verbose with assertions?
No, I personally would think that so in languages which exhibit flexibility in their typing discipline, but where the code actually imposes strict constraints on what would be implicit constraints on what is a legal type to pass in, I would say testing those things up front, if you could include, assuming that the assertion mechanism allows you to include a meaningful error message if it's violated, I think that could be very helpful to do. Among other things, Alex, what it may prevent is, the worst case here, why would you do this, folks? Okay, so suppose you have some code. Let's reason through this as a class. Those who are not using electronic devices. If you have code which has some implicit dependency on certain methods, for example. So you have this method called foo, and it takes an argument of type bar, and And there's some code here, and hopefully it's short. Hopefully it's not a lot more lines than 10 in this code, because otherwise it'll give me the willies when I'm grading it in the final marks for this class. Suppose we call b dot zap. You know, here we call this. Why might we want to verify? And you know, maybe this is maybe this is a poorly typed language. All we take is a B, right? And all we do is call a zap. Ladies and gentlemen, I don't want to shake your sense of the world, but there are languages which allow you to do this. Which what's that?
Yeah. It is nice in a consistent language like Python. In a broken language like PHP, it's a nightmare.
Indeed, and JavaScript, it can be a nightmare at times too. Well, I wouldn't call it exactly duck typing. I think it's more mixed bag. There's many languages where you can specify sort of loose typing or no typing at all. And why might you want to put an assertion here to the effect that B is something of some known type? Why would you want to do that? After all, I mean, you're calling zap on it here. Isn't that enough to sort of verify that it's of the correct type? Why does putting an assertion in help? Good.
Make sure we're getting type B zap.
Right, because the semantics of zap may be different. Zap is a word which exhibits linguistic flexibility, and it might mean different things in different languages, or different classes, different contexts. So that's one reason. That's good. Another reason is an assertion might have a message. Another reason is, ladies and gentlemen, in a given set of test cases, you might not hit the zap. I've written this in a fashion that that would suggest straight line code, but in fact, this might be buried within an if and another if and a certain while loop, and you may be running test code that never hits this case in your program with passing it an argument that this won't be able to happen, and you just haven't tested it enough to reveal this. If you put it in an assertion, that makes your assumptions explicit and checked up front, which can prevent test escapes, situations where the testing does not reveal this dependency until it's sitting in front of your user. You know, a prominent biologist, molecular biologist, using your system, who's been putting all her data collected from around the world into your system, and suddenly it breaks and becomes unusable because a test escape occurred, which corrupted the database. Yes.
I was just gonna say, like, isn't that kind of cheating in a way, because like you're supposed to, if you're gonna test properly, you want to test everything in the code. So I mean, yes, that's going to be the problem right away after this one, but that's also going to be maybe even one test inside of that loop. I think it's you're testing the type versus.
Yeah, you're testing the type. You're still going to need to exercise it fully.
Suppose the zap is located within an if statement that only executes under the string.
You still have to test it, you know what I'm saying?
You should, but not necessarily, because you know we don't want to state that.
Well, let's put it this way. If it's going to fail, you want it to fail as early as possible. And you do definitely want to push. It's true, you don't want to give up early, but that can be said about any sort of testing. You know, you put this test into place, that may lead you to not put other tests into place because you have undue confidence or something. So I do think the point is a very strong one, that it may be that zap is hit only in the case of weird network congestion. You were never able to replicate that in your testing. So these things do occur. If you have polymorphism in your program, you should perform very heavy testing on that to exercise superclasses and subclasses as well. So in other words, you should test code written against superclasses. Even if they don't mention your particular subtype, you've got to test it with your subtype to make sure it works properly. Because you add a new subtype, it's not guaranteed that that code written against the supertype will work, because there's no checker in the world right now that's going to fully check compliance against the list of substitution principles. Okay. And if you have code, please don't show this to me. Please don't show this to me. Code which explicitly checks all possible types of a parent type, of a super type, and handles each of those types separately. You're going to especially want to check against that, because that's broken. When you add a new subtype, it may not be handled. And not only are you going to want to test that, you want to fix that, ladies and gentlemen. If you folks see in your code, in Java, if you see an instance of, if you see that in your code, like test that A is an instance of B, I'm not putting on the syntax for doing it, but there's a way to do this in Java. You better be doing something pretty unusual. Like maybe you're doing something with reflection, and there are times where you'll want to do this under certain circumstances. But for most cases I have seen of this, is A an instance of a certain class B? A an instance of class B. That's an indication that you're not exploiting polymorphism. It's an indication that you're doing something that is not going to be very sound with respect to object-oriented programming. You should be instead asking, for example, you can be calling a method on A, which is defined differently in different subtypes, etc. But if you see this in your code, it's a warning sign. It's a warning flag. I will zero in on that in your code and scrutinize it. If you want to read more about this, I would check out Fowler's book on which discusses bad smells in code and refactoring. And this is one of the bad smells in code. I'm hoping I won't have many bad smells from your code.
Is it too late to drop the class?
So one of the uses of tutorials that I'd like to make in this course is to go through code from the systems. And I'm thinking this afternoon might be a good time to go through some code. You want to do it?
Yeah. Yes, please.
Okay, 4 p.m. Be here or be square. Well, I would encourage you to be square in any case. But that's just.
What does that mean?
Well, most people.
I don't actually know what that means.
Seriously?
Square. No, I don't. What does it mean?
I think.
Physically make yourself.
Okay,
square.
maybe your notion of square is different from mine, but I'll write it off to generational differences. Moving right along. Okay. So fraudulent subtypes are a big risk associated with object-oriented programming, and I will expect you to be checking the correct operation of code written against parent types against your actual types. Subclassing is another whole issue. Subclassing involves not only subtyping, as we know, not only subtyping which brings along polymorphism, but it also involves what, ladies and gentlemen? What else does it involve? Yes, you can look at the slide rather than small electronic devices. Yes, it involves inheritance of implementation. It involves reuse of how a type is implemented. You can have A be an instance, you can have A be a so class A be a subtype of class B without any extends relationship between them. You can have A be a subtype of an interface, for example, in Java. So it's passed around as if it's something that implements that interface. You folks comfortable with that? That's subtyping? Yes or no? Speak, use.
A little bit unsure on the difference. So subclassing necessarily entails
Subtyping.
reusing. Okay, yeah, it entails subtyping, but it also entails reusing implementation, whereas subtyping does not.
Correct. Does not necessarily involve use implementation. by in and of itself require it. There's lots of subtyping through subclassing, which does involve reuse of implementation, but there's lots of subtyping that does not involve reuse of implementation. Maybe because what's being subtyped is not itself a class. It's an interface, for example. Right? Yes?
I got confused there. Could you draw like an A/B example?
Yeah, sure.
I'm actually serious.
Sure. So I'd like to have the class participate in this. So
Is it possible to have subtyping with inheritance that isn't subclassing?
not in Java. Not in Java. They're mixins, which are supported in other languages, and I used to talk about them in 470, but and I mentioned them in one of my earlier lectures. They provide, so some languages provide this concept called mixins, which gives you essentially something very much like subclassing, but without subtyping to go along with it. It lets you kind of mix in a bit of functionality from this class, a bit of functionality from that class. In other words, use the implementations of them without pretending as if you are one of them.
What's an example?
Smalltalk actually had a sort of the capacity to do mixins, if I'm not mistaken. A more modern language, just trying to think here. No, I'm coming up blank right now, but you will find it. Yeah. And if anyone wants to look it up in a small electronic device, they're most welcome to, and share it with the class. Okay, so give me an instance of subclassing in Java. Every object you create is a subclass of what? Of object. Yeah. So you create my class, and that's a subclass of object. What does that mean?
My class is of type object and also inherits all of its methods.
Yeah.
Like is equal,
Yeah.
hash, or
That's right. So all of the methods that are implemented in an object, you have at your disposal my class, right? And you have in my class as well. Unless you override them, in which case you have your own versions of them, right? You comfortable with that? All of the fields which are in object are further available in my class. They're all there. All that data, any data that's provided in object is provided additionally in my class. So all that data that's in an instance or that's specified in the class of object is available in an instance of my class. Does that make sense to people? All that implementation comes along with this subclass relationship. And in general, if you have A being a subclass of B, A inherits all the implementation of B except whatever it's overridden. So it gets all the data. It gets all the methods. It not only has to adhere to the promises of that superclass, it gets all of its implementations of it. It's like me setting up my FedEx franchise and buying into all the computer systems that FedEx provides. So I don't have to build my own computer systems now. I just use the FedEx computer systems. I don't have to buy my own, vans to take the stuff to the airport for various flights. Those are all provided to me. I'm using all of the implementation associated with FedEx that FedEx provides. There's great power in that. But as we'll see, there's great danger in that. Okay, I'm going to contrast that with subtyping. Give me an instance of subtyping in Java, a concrete instance of subtyping that does not involve subclassing. Okay. One interface extends another, yes. And I would argue one class extends an interface. Do people understand what I mean by interface in Java?
extends an
Implements an implements an interface. So give me an instance of an interface in Java.
Q.
Yeah. Okay. Good. So there's quite a few associated with abstract data structures. In fact, I saw some earlier. If you look back here, these ladies and gentlemen are where are the interfaces in this diagram? Exactly. Yeah, these sort of there's probably a geometric name for them, but rectanguloid type denotations. Okay, so these are various subtypes, and priority queue is a what? Is that that's a class. It's a class that implements queue. Now, here, priority queue is a subtype or subclass of queue. It's a subtype. Does it inherit the mechanisms of queue? Does it inherit the implementation of queue? That's partly a trick question.
Well,
There is no implementation. So it doesn't inherit the implementation. It just can be passed around like a queue, right? So we could have a queue here. Maybe I should draw it in the same rectanguloid fashion. And then we can have a priority queue, right? I'm omitting the generic syntax. Maybe you could consider me pre-Java, what was it, 1.4, what have you, where they rolled out generics. So here's a priority queue. This is a this is a class which implements this type. It's a subtype of this. We can pass it around as a queue. It has to adhere to all the promises of queue. Its promises have to be consistent. But it can provide its own implementation for all the methods declared in queue. Queue has methods like poll. Queue has methods like get, or methods like pop or what have you to remove the item, remove. And priority queue has its own implementations of them. It would be as if I set up a FedEx franchise here in town, and I told FedEx, look, I'm not going to use your computer system. I'll send you all the information, the packages I ship and so on, but I'm going to create my own computer system. I'm going to have my own vans take the stuff to the airport. I don't need your mechanisms. I'll adhere to your contracts. I'll adhere to all the FedEx promises, so the customers will be happy. They're working with honest to goodness FedEx, but I'm not going to be reusing all your mechanisms. Maybe I have some special way of doing it cheaper. You know, I have some special ins that allow me to do it at a cheaper rate or what have you. Or I'm clear about what I need for my computer system, and I have more computer experience than they do. So here we have an implementation which needs to observe all the promises of queue, but it is something which doesn't reuse the mechanisms. Does that make sense to people? Yes?
Yeah, but see, isn't it the same as like overriding all the methods in my class?
No, it's actually not. It's close. You're onto something, Logan. It's close. I think what you're saying is, okay, imagine my class is a subclass of object, and it just overrides all the methods, right? It replaces all the methods of it. There is something else, though, that's used here that doesn't really carry over well to the FedEx example. All the data that's in here is also in here. You can't override that. All those fields are ended up being reused. Hmm? They're at a binary level. They're going to be part of my class. Yes.
They can't be accessed by this.
Correct. They can't be accessed by it, but they're there, behind the scenes. Ignore the man behind the yellow curtain. So this inherits all the mechanisms. Whereas when we have an instance of subtyping, it doesn't necessarily imply reuse of mechanism. In fact, here there's no mechanism to be reused. Now, Java doesn't happen to support it, but you can imagine one subclass being, a class being a subtype of another class without being a subclass of it. You could imagine it. It just has to adhere to all the promises of its public interface, anything that someone could be counting on, but it implements things de novo. No, because for the most part, the methods in the abstract classes are in fact reused in the subclass. That's a lot of the reason abstract classes are used, is because you provide a partial implementation in the abstract class, which ends up getting reused in the subclass. But you could, in principle, have one class be a subtype of another class, not reuse any of the mechanism. It doesn't get the fields. It doesn't get the methods. But it adheres to the same promises. So if you're using the devices back there, look me up a language that supports mixins.
That's what mixins are? What you just said?
No, mixins are a way of getting the benefits of subclassing without having to imply subtyping, which is another way of decoupling the two. Okay. They allow you to take a little bit of this mechanism, a little bit of that mechanism, without in any way promising that you adhere to the promises of those things that you're mixing it in from. So, for example, I might have a class which uses a mix-in serializable, and I just mix in some of that. It gives me a field which keeps my ID number, serial number, etc. Or serial numbered, and then serial numbered class, and so it provides a bit of implementation I can reuse, for example. Yes. Great. Yeah, Python.
That's cheating.
Well, okay, but maybe it supports it at some form, but appreciated that. That's much valued information.
Easily to get spaghetti code though, if you're just grab implementation from components and just restrain code. It just doesn't seem.
Yeah.
Can't see what implementations to grab implementation.
Yeah, I mean, you can have sort of things that it eliminates the need to create sometimes utility classes and stuff like that, which could just be grab bags of functionality. So it's not that, it may just shift the ugliness. I don't know if there's conservation of ugliness. This is one of the questions. My conjecture is there exists no conservation of ugliness. In fact, it is possible to have systems which are created in languages where it'll be much, much more beautiful. I will assiduously stand by that comment. If anyone needs validation, I would suggest that you write string processing code in Fortran and compare it to the same sort of code written in Snowball or written in Ruby. I think you will see the difference, and perhaps, ladies and gentlemen, see the light. Okay, so subclassing. Subclassing involves not only subtyping. Not only can we pass around this priority queue as if it were a queue, but it as subtyping would provide. Excuse me. This is subtyping. Subclassing. Not only can we provide my class as an instance of object, but it moreover inherits it. Right? Yes, Brian.
I was going to ask there. The priority queue just doesn't have any of the implementation of queue, but it's treated as a subtype.
It's a subtype of queue, so it can be passed around. Subtyping, ladies and gentlemen, gives you polymorphism. Subclassing gives you subtyping, and it gives you reuse of mechanism. But, ladies and gentlemen, that leads to extra complications. So here, for example, we saw earlier a subtype hierarchy in Java. There we go. There are subclass hierarchies in Java, such as this. Piped writer and object, for example. Here we have subtype hierarchies. Now, the risks here are of a couple sorts. One thing is that you could violate the Liskov substitution principle. So the subtyping is wrong. The promises of your subtype, say print writer, may not adhere to the promises of a writer. And that's something we covered before, Liskov substitution principle. you want, ladies and gentlemen, you want to test those principles for the subtype to make sure they're consistent, to make sure that the promises of the supertype are maintained. Okay, so that's this whole thing about testing for fraudulent subtypes. But the second problem is that the implementation for a subclassing may fail to capture the intended behavior. So not only do you have to worry about inconsistent promises, you have to worry about, do you actually achieve those promises? Thirdly, you have to worry about being a fragile subclass. So the subclass can depend on the implementation details of the superclass. And when the base class is modified, your subclass may break. Or you may break the sort of mechanisms in the superclass that you're counting on as working. Okay, so we talked about how extra information, for example, is needed. Remember this add and add all case? Whether or not that worked depended on what? Remember this case? Yeah, the implementation of add in the in this. Excuse me. That is actually. Yes, correct. So the question here is, if we wanted to maintain some extra information beyond what's maintained in this hash set, such as the number of things we added, would we just have to override add, or we'd also have to override add all? Do you remember that? And it depends. It depends on whether add all up here ends up calling add to do all its adds, in which case we'll be calling our add, right? I want you folks to be, if you folks graduate and you're not clear about this mechanism, you're going to be just asking for trouble. You need to be really, really clear with this. So if I have an instance, ladies and gentlemen, of instrumented hash set, if I have an instance of instrumented hash set, we'll call it IHS, and we'll call it I, maybe we'll call it S. So if I have an instance of that, let's suppose that I haven't overridden at all an instrumented hash set, okay? I haven't overridden it, okay? Ignore what's on the screen. So I haven't overridden it. And I have an instance S of instrumented hash set. And I call its add all. Whose add all is called? Hash set's add all is called because I haven't overridden it. Okay, now suppose add all in the hash set calls add. Whose add is going to be called then? So I call s.add all, so it's calling off to the add all of, so when this happens, we're calling off to hash set dot add all, right? I'm almost drawing the call stack here. Suppose this add all in hash set calls add. Which add is going to be called? Yes. Ladies and gentlemen, if you're not clear about that, either raise it now or come to office hours. I will be glad to spend hours with you to make sure that you are clear on this. It's not a silly thing, but it is absolutely essential if you're going to be using object-oriented programming that you be crystal clear on why this is. And it has nothing to do with about intelligence or whatever. It's just understanding the conceptual framework about how this works. I'd be happy to work with you very closely to make sure you understand this. So hash set here is when it calls its add, it is going to be calling instrumented hash set dot add, because that's been overridden in our instrumented hash set. And we're dealing with something that's truly of type instrumented hash set. As a result of this, you're going to be calling this add here, right? And here we keep track of the number of things added. Now, if on the other hand, the add all in hash set does not call add and just goes and adds things in directly to the set S that's maintained internally, to some set that's maintained internally, then we will not be, our add will not be being called and we will actually need to separately keep track of the added items being added in. And we could have done it by adding in this add all ourselves. Does that make sense to people? So what I'm saying is, this subclass, whether or not it's correct, depends on the vagaries of how the superclass is implemented. And the thing that's difficult here, folks, and please remember this, not only for your final exam, but ladies and gentlemen, for your career, is that the superclass may evolve without us. We may not have created the superclass. The superclass may not be visible by us because it's in a jar file shipped by Sun or by some other party. And we don't have access to it. And the next version of Java, maybe add all does not call add. And before it did, our code tested fine, and now it doesn't. This is what I mean by a fragile subtype. This may have worked clear as day with the earlier version of the JVM. New version of JVM installed with the JRE, new updated JRE, and suddenly our code is broken because add all in the superclass no longer calls add directly, it just does the internal work. You would hope that those would be internal details we don't have to worry about. They'd just be implementation details of what's going on inside hash set. But ladies and gentlemen, this is nothing short than the burden of subclass. This is nothing short but the yoke that we put on when we subclass an object. We have to worry, ladies and gentlemen, about parts of the implementation of the superclass. We are bound to the superclass. We have tied our fate to the superclass. And as the superclass evolves, so must our own code base. And this is why that link to the superclass, while it brings power, I'll get to you, Brian, and while it brings functionality, ladies and gentlemen, it brings risks as well. And you must be cognizant of those risks, and you must guard against those risks through assiduous testing, as I'm hoping that all of you are doing for your final deliverable. Yes, Brian.
You just threw me off. No, I was just going to say, so this is strictly based on the uncertainty of the implementation, whether or not it's correct.
Well,
because you said that in one version it could call the internal add,
yes,
and then in another version it could call more add. But that's uncertain, right?
No, let me clarify that a little bit. You may be clear about it, but I want to make sure the class is clear about it. In one version of hash set, add all may call add, right? And if we test this, it works just fine, the hash set. In another version of add all, it may not, and so a subsequent version, say the next version of the JRE, add all does not call add, it just does the work that add would have done by adding it directly to the internal data structures. So it doesn't bother calling add, it just internally does that work. Maybe it's inline the call to add, for efficiency reasons, or it's directly frobbing the data structures that add would have called, but it does it in an intelligent way, taking advantage of the fact we're adding many items at once, so it doesn't have to do a lot of additional mechanisms. That code would be perfectly correct by itself.
Yep.
What breaks is our code, because we wanted to guarantee that we were correctly keeping track of the number of items added in to this hash set. And it used to work, maybe if it did call add, and now suddenly the superclass has shipped a new version, which also works for it just fine, but it's broken our code.
And it would be breaking our code in the sense that it ends up calling our add on IHS.
So earlier it was calling our add, and now it is no longer calling our add. And so we have to override add all to get it to maintain this extra information on that account. Does that make sense to people? Yes,
When you compare things like that, like other than correctly, like it should be because it seems kind of unintuitive how if they change something in there to the class, how would you know that?
Okay. So this is a good question. The truth is, in a lot of situations, the correct way to do it would be for the superclass to provide a contract that's different for the subclasses, to provide extra information as needed to build subclasses that look, add all will always call add, okay? Or they could say there's no guarantee that add all will call add, in which case you will build accordingly. I mean, this is part of the problem. You don't know whether or not it will call add. If you err on the side of thinking that it will call add, and you put this code in place in the subclass without overriding add all, it may break in the future, right? If on the other hand they said add all is not, there's no guarantee as to whether or not it calls add, which is the default case, you will need to override it. And you will need to override add all as well, just to be safe. You'll need to, okay, I have to be careful here. Excuse me. What you would need to do, I stand corrected. What you would need to do is actually implement. It's even worse than that, because the problem is here I've forgotten we're delegating to the add all of the superclass.
Yeah.
And if we're doing that, it's kind of damned if you do, damned if you don't. Because if you don't know whether or not it calls add, if you think it does call add, maybe you test it and oh yeah, it's actually calling add. And so you then say, okay, we're going to go with this implementation that's shown on the screen here, right? Excuse me, you're going to go with the implementation which does not override add all in that case. Or if you verify in the existing JRE that add all does not call add, you will put in place the mechanism shown here. Either way, it could break, right? The way to handle this is for the superclass to promise what is guaranteed about what calls what. And then you can create something with confidence that won't change. It's telling you what you can count on from now on.
What does Sun do that though?
Some cases, yes. Now, if it doesn't, what you could do is not inherit.
But you need that class from Sun. Like you need
What?
I don't know, like whatever your program's doing, you need that.
It's a convenience.
Okay.
You shouldn't be slave to Sun.
Okay, yeah.
You shouldn't be a slave to Sun.
That is very true. That's what they want.
Sun, don't be a slave to Sun. This is the burden of subclassing, and this is why subclassing imposes risks. And this is why when a new JRE comes out, you will need to test your code especially thoroughly. And you will want to put into place in your set of regression tests that will routinely check these sort of mechanisms to make sure your code is still working. Because the rug could be pulled out from under us. We are depending on something outside of our control. So, even if we have access to the code, even if this is an open source system, we say, oh, we can go see whether it calls add all or not. Does that solve our problem?
It's still wasting time.
It's wasted time for the first thing. It forces us to grunge into code, which we have no particular interest in. That's one thing. But also, there's no guarantee about how it will evolve in the future. Maybe in the future, someone will go and have it not call add. Add all will just function internally to add it. And so we're in bad shapes for that. I want to leave you just a second here for your group meetings. I talked about the yo-yo problem. The fact is that when we have code that overrides, we often get a situation, particularly in deep type hierarchies like this. If we have code, for example, an input stream writer, which overrides some methods, you may call a method there. That ends up calling off to a method which is implemented in object, well, it's typically not going, well, sometimes it may call off to a method which is implemented like toString, which is implemented down here in input stream reader again, which may call off to a method which is implemented in reader, and then once again down in input stream reader. And this leads to mixing of code implemented by different people at very different times, sometimes with different assumptions. And that also complicates the challenge of testing it thoroughly. So here we have this sort of bouncing up and down associated with the code being executed. It makes it hard to do full inspections of what code is going to be called. Normally, if you're conducting inspections, as I hope all of you are doing for this next deliverable, remember everyone in here is required to undergo an inspection for at least one artifact they create. Remember that? I sense sudden agitation, sudden movement on the part of people in the class. And, better late than never, and better Nate than lever as well. So when we have quality, if we want to achieve quality subclassing, there's a few recommendations. We want to perform thorough inspections of subclass code, but remember that the code you want to look at, the interfacing code, may be in superclasses. Okay, clearly specify distinct subclassing interfaces that are different from instance interfaces. Designed clearly for subclassing or prevent it by making a class final, for example. And there's tools called class flatteners that will actually take a class that's a subclass and basically show you all the things that are involved in that class, wherever they came from up the type hierarchy, up the inheritance hierarchy. It will show you where these mechanisms came from. Let's talk about testing for subclassing. Run standard tests for subtyping. Please do that. Continue running unit tests for subclasses, even if you've only changed, for superclass, even if you've only changed the subclass. So run those unit tests on instances of those subclasses, because you might have broken the superclass functionality by overriding something in the subclass. I've seen this before. Something used to work in the superclass, code declared by a superclass, now it's broken because it calls off to a method in your subclass that doesn't do the right thing. Test mixtures of subclass and superclass functionality together. Heavily test overridden methods, even more so than your average method. And changes to superclass code should cause testing against all, ladies and gentlemen, all implemented subclasses that you're using in your program. If you're frobbing that superclass, make sure that you test it with other subclasses. Confirm proper initialization of superclasses. Make sure, particularly in languages like C++, that you haven't neglected to initialize the superclass. And if you're going to override the methods in the subclass, you want to retest other subclass and superclass methods. Separate issues have to do with type parameterization, ladies and gentlemen. If you have a parameterized type called a generic in Java, templates in C++, they go by various names. They're called type parameterized types and type parameterized types, for example. You will want to be sure to test that with a bunch of different type parameters, a bunch of different possible things. So this would be a list of X. Test it with the different X's you use in your program to make sure it works properly. In some languages, you may find that those errors are hidden until runtime. Okay? So those are all my comments on